Okay, I wanted to talk to you a little bit about the history of databases. There's not a huge amount I'm going to talk about the history, but we are going to cover some things because I think they're relevant to things that are going on today. And quite often, if you don't know where you came from in history, you end up back at the same place, and that's not necessarily a good thing. So, ACID compliance. ACID is an acronym. We're going to get to what that is. But let's talk about the early history of database management systems. And really, this is Charles W. Beckham in about 1960. 1960, he developed the first database management system, the Integrated Database System, IDS. And he was really critical not just in developing that, but he took this common business-oriented language and standardized COBOL to work with IDS. And this was a very popular system for a long time. Lots of things used it, especially banks. And to give you some clue as to how common COBOL was, in the year 2000, there were good estimates that showed that about 60% of all software in the world was written in COBOL. So, COBOL is still around. And you see it in a lot of banks, you see it in insurance companies. There are still major applications running to this day in COBOL. And there are things that predate COBOL. COBOL is the common business-oriented language, and there are things that predate COBOL, like, for instance, JES2 on an IBM System 360 is what it's from, IBM System 360. Is still in production today, and all that stuff is written in assembly language and basically uses the successor to IDS, which IBM got involved in, and they built a system, the Integrated Database System, or Integrated System for Database, IMS, the Integrated Management System. Okay, that was from IBM. And they designed this integrated management system specifically for a certain project, but lots and lots of things used it. And the project that they built it for was tracking of inventory and supply chain for building the Saturn V rockets, so the moon rockets. All right. Now, lots of things use these. And the way that these things worked is you had a particular chunk of data, and that particular chunk of data would then have pointers that would lead you to other chunks of data. Okay, and this system of pointing was generally a combination of a file and an offset from the beginning. So if this was in file 1, you'd have over here file 2, and at some offset record location in here, you'd say that this is in file 2 at position 3. And so that would refer to that piece of data right there. Now, this network database concept, I built software in the 80s, in the late 80s, using a network database. It was still around, but it had become out of favor. There were advantages because this is a fast way to access stuff. Now, IBM, in its infinite wisdom, had lots of stuff like this, and consequently, they wanted all the files to be fixed-length records. And in about 1970, some people went, you know what, fixed-length records are fine, they're efficient if this is the way you want to access stuff, but in reality, what we see is that most fixed-length records are 80 characters long this way, and they're text, and really the text is quite often very short. And they actually went out and measured stuff, and these people figured out that somewhere between 60 and 80% of all of this stuff was the blanks at the end of the line filling up useless space. And they invented a system called Unix that is still around today. A few of us use it. The underlying system behind Linux, and it's all variable length records. But, the people at IBM were really thrilled with the fixed-length records because 60 to 80% blanks meant that they sold a lot more hard disks. And if you're in the business of selling hard disks and 60 to 80% of your space is wasted, we call that profit. So, yeah. In any case, that's what that was based on. That's how it actually worked. Now, this network database concept has not died, because like I said, it is efficient in a certain sense, sort of way, as in, if I go to this, I want to find the things that it's related to, I know exactly where to look, because they're all stored up here. But if I add something new to it, it becomes very difficult to update the information here and down here at the same time. So this caused all sorts of concurrency and delay problems. One thing trade-off for another. But those concurrency and delay problems in about 1970 led a guy by the name of Edgar Codd, C-O-D-D. He was an IBM researcher in their disk and how these disks were used. IBM Watson researcher that was a storage research person. To write a paper, you should probably go read it. It's not exactly the most current, but on the same time, the concepts haven't changed, and it's the foundation of almost all database stuff you're going to see today. And in that paper, he did two things. The first one was he suggested a structured query language. His original structured query language evolved before it became a standard, and the other one was ACID compliance. And the combination of those two things are what we deal with today in something like Postgres. It's an ACID compliant database, and it runs a somewhat modified, it did evolve over time, but SQL was standardized based on his original research, and this system over here for COBOL and the network access system over here eventually fell out of favor for some very good reasons. So, these two things are critical, especially ACID compliance if you're doing financial transactions, because it guarantees durability, it guarantees serializability, it guarantees that if you do the same thing again, you're going to get the same results the next time. So, we've been doing a lot to learn SQL, but there's this underlying thing called ACID. And ACID stands for atomicity. Atomicity? I don't know how you pronounce that word. It's atomicity. Basically, it means that if I've got a insert, an update, and a delete in a single transaction, that these work in an atomic fashion. I can start a transaction, I can do the insert, the update, the delete. If something goes wrong in the middle, all of it fails altogether or all of it succeeds. And these transactions, okay, have to work so that they are atomic, as in the data that you see at the beginning of the transaction is the data that everything is working on in the middle of the transaction. It doesn't change in the middle. So in our Postgres database, the moment a transaction starts, all of those things that other people may be updating concurrently are invisible to this transaction until the transaction finishes. And that's hugely important for testability, for reliability, and it adds a lot of complexity. Let's face it, this is not a simple thing to do. Consistency. Consistency is basically, if I start out with a database in this state, and this is the state up here, I end up with a new database in state 2. And if I started out with the same database in the same state, I would consistently end up in state 2 for whatever that transaction is. There's no gray area where it doesn't transform the data consistently from this, through this transaction to this new state every single time. Isolation. Now remember, part of this consistency and isolation is that there are multiple people hitting the database at once. So with all these different connections going on and all these people changing data, okay, this transaction has to be independent from everybody else. It doesn't interact with other people in the middle of a transaction. It doesn't see their data. It doesn't know about their data. In fact, there's been some really good research over the years to show that lack of independence, of isolation in ACID, makes for untestable systems. If they aren't isolated, you can't test them at all and get consistent results at the end. And the last one is durability. Durability is an interesting thing. Let me give you an example of how hard durability is. Oh, man. Durability means that when you get done with that transaction and the data is written, the data is actually written to disk. It's saved consistently. It means that you have ways of backing up a system so that you can recover if hard drives, when hard drives fail, when computers fail. That's what durability means. Now, this is something that most people don't know about Unix. But you go to write a file in Unix and you do some file operation write. And you're going to write 1,000 bytes. Some string, some buffer that's 1,000 long. Now, in Unix, you would think that you write it, it's written to disk, at the end, the function returns from the system, and the data is actually written. But that's not actually what the operating system does. You see, operating system calls like write are interruptible. So, write returns the number of bytes that it actually ripped. So let's say you call it, and somewhere in the middle of this operation, it gets interrupted, and it's only written 104 bytes out of your 1,000. So it says to you, I got 104 done, here it is. Now, it's up to the application to be able to say, oh, at this point, I have to recover. Something happened, it got interrupted, I've got to write the other 896 bytes still. Remember durability? That process of being able to accurately write and get the data to the disk is hard. Very few people ever deal with that. Now, you look at something like MongoDB, it has not dealt with that. It took decades of development, literally, in these databases to get these processes that guaranteed durability, isolation, these ACID things to actually work. And not just a few people worked on it, a lot of people worked on it. And in the 80s and 90s, there was consistent problems in databases like IBM's DB2, Oracle, where there would be cases, edge cases they hadn't dealt with. For years, these big companies had trouble getting to this point where they could consistently write it. Now, let's say that you've got a computer out here, and that computer has got a set of disks, but you'd really like those disks to have a buffer in between that's in memory so that they write faster. Now, there are lots of controllers that do this, and you can buy this and set it up. It's pretty common, but if you want to maintain your ACID compliance, that controller and those disks have to have a battery backup. So if this computer checks out and fails, the information still gets written to the disks. So it has implications on what kind of hardware you use. Now, are these things guaranteed in every system running on Amazon Web Services that your disks are battery backed up, that you can actually tell when stuff is written, when the computer sits over here and it works across the storage area network to another disk system over here? Those are good questions. Good questions that I don't have good answers to. In things like MongoDB, the consistency guarantee is a thing called eventual consistency. Eventual consistency means that you don't necessarily have isolation or durability. It means that eventually there will be some level of consistency in the data if the computer keeps running and two people don't access the same data at the same time. Now, in other databases, and specifically I'm thinking of Cassandra from Facebook, it has durability, okay, and it also uses eventual consistency, but it doesn't have isolation or transactions that are completely guaranteed to be isolated, as in sometimes you're going to see other people's data, sometimes you aren't. All it guarantees that eventually the data will settle on a certain state. So these databases tend to have underlying problems. Now, as time went on and people did stuff with this, the people that actually went out to find out if this was working was Google. And remember, we've got these network databases that we decided were a bad idea a long time ago. Okay? There's some good things about it. Cassandra is a network database under the covers. NoSQL databases fall into many different categories. MongoDB is a document store. Okay, and it has eventual consistency, which means it doesn't have durability. Google built a lot of software, and they actually put a research group together to find and track what the causes of their errors were in lots of this software. And what they found is a common cause for their errors were that their NoSQL databases didn't have ACID compliance, but the application still had to implement that stuff. And remember the decades it took to get this right? Quite often, it wasn't implemented right. That inconsistency and the lack of ACID compliance was a big cause of their errors. And they went to the point where they just internally banned the use of NoSQL databases. Their exception is Redis, which is a NoSQL database, sorta. It's more of an in-memory data structure. But it's not used like a database generally. It's used for things like high-speed buffers between computers. It's not generally used for storing data. But things like MongoDB, they just out and out banned it in favor of this other database that they built called F1. I've got a link in the notes to the paper about F1. They call it the world's first world-scale database. At the time when it was first being used, their version that's in production is not F1. It is a revised version that's had a bunch of revisions. But they built it originally on top of 14 data centers with atomic clocks that they spent $500,000 on each clock to synchronize it. So, they spent a lot of time, but they banned NoSQL because it doesn't have that ACID compliance. Now, you see a lot of these things with network databases coming back, and there's entire classes of data that work on this network database principle, like most blockchains. It has its good points, as in, yes, it is fast to access from one block to another block, especially in a blockchain where the blocks are basically added linearly at the end. Okay, but it has disadvantages that are very noticeable. Okay, in Ethereum, because you also have access to data that's not just necessarily in that block or the previous block, it also keeps a hidden out there store where it keeps track of data that it's visible, that you can see, that isn't stored this way, but comes from the blocks themselves. So, they kind of do and they kind of don't, but it has its own performance problems because of this network model. So, COBOL today, it's still around. These basic ideas are still out there floating around. Lots of COBOL exists. Pre-COBOL, like IBM 360 Jest 2, your taxes are running in assembly code that's based on that. These things don't go away. We just build new things. We don't necessarily go back and fix all the old ones. So those old ones are still out there. And you still see stuff running on these other databases, even though, they've by and large fallen out of favor. But the key pieces to take away from this is really that we've got ways of synchronizing across big systems. We know what the pitfalls are and how to take care of them with compliant systems, and those compliant systems are really fast and really reliable today. And we can, if we choose, learn not to make the same mistakes we made in the past. So that's a big part of the reason why I'm not touching much on MongoDB, even though it's quite favored by a lot of people, is because it doesn't have this. The other reason why we're going to touch on MongoDB, there's an interactive homework that covers some of this. We are going to have a lecture on MongoDB, is because everything you can do in MongoDB, you can do in Postgres using JSON and JSONB data. And along the way, Postgres has a relational database attached to it. So you can do a bunch of things Mongo can't do.